Okay, chemical vapor deposition, as the name CVD implies, you see from the view graphs that it is the chemical vapor deposition, or in short it is the CVD, is the formation of a non-volatile solid film on a substrate by the reaction of vapor phase chemicals. These vapor phase chemicals, basically they are the reactants that contain the required constituents. So, one thing is that you have to have a substrate on which the film will be deposited, and there will be chemical reaction, and this vapor phase of the chemicals, they will be subjected to some reactor which is known as the CVD reactor, and then chemical vapor deposition will take place. The reactant gases are introduced into a reaction chamber and are decomposed and reacted at a heated surface to form the thin film. So, another important point is that there must be a heated surface, that means the substrate must be heated. Okay. So, one thing is that you must have a substrate, second thing is that the temperature will be high, because the substrate will have to be heated. So, on the substrate there will be some decomposition of the constituent chemicals, right. Suppose you want to make a silicon film. So, then what you have to do? Then you have to have some chemicals containing silicon, say silane. Silane is a chemical containing silicon. That silane will have to be injected in the reactor chamber by means of some vapor. So, you have to make vapor of that silane, you have to inject it in the reactor, and there must be a heated surface, that means there must be a substrate. For silicon thin film, generally the, if you have to make some epitaxial film, then what should be the substrate? Silicon. For silicon, what should be the substrate for epitaxial film deposition? Silicon. The best option is to use the silicon. Then you have to use the silicon substrate, and then you can have silicon epitaxial film in it. Now, this chemical vapor deposition, which is also known as the vapor phase epitaxy, you see that it is also known as the VP, vapor phase epitaxy. So, that means that when you like to make some epitaxial film, then it is known as the vapor phase epitaxy. Otherwise, conveniently you can tell it as CVD, the same thing. Only thing, the only difference is that if you used to make some epitaxial film out of CVD process, then that is known as the VPE. Okay. So, one important aspect of this CVD is that you can make epitaxial film out of CVD, because we are discussing about the epitaxial techniques of film growth, and in our last class we have covered liquid phase epitaxy, and in the next day we shall cover the molecular beam epitaxy. Today we shall devote our attention on the chemical vapor deposition, or the CVD. This CVD can be of three types. You see that one is APCVD, or the atmospheric pressure CVD, another is the LPCVD, low pressure CVD, and third one is the plasma enhanced chemical vapor deposition. So, broadly you can divide CVD into three types of techniques. One is LP, low pressure, another is AP, atmospheric pressure, and third one is the plasma enhanced. So, as the name implies, you see that in atmospheric pressure CVD, your CVD reactor will be in the atmospheric pressure. Okay. So, what do you mean by the CVD reactor? CVD reactor will be a quartz tube type of thing. Okay. It's, you have seen the reactor for the diffusion, you have seen the reactor for the oxidation or ion implantation. So, almost the same type of thing. Say this is your quartz tube reactor, this is a reactor. Here this is the susceptor. What is a susceptor? Susceptor is basically the equivalence of crucible in bulk crystal growth. In bulk crystal growth, we have used the crucible. Here we do not use the crucible, instead we use the susceptor. Susceptor is a graphite block. It is a graphite block on which the substrate is placed. Okay. So, now one question arises that if your gas or the vapors contain oxygen, then whether you can use graphite block as susceptor? No, you cannot, because at that temperature oxygen will react with the graphite, right. So, if you use a gas or a vapor which contains oxygen, then what are the susceptors you can use? Material? No, it is basically the stainless steel which are used, one thing. Another is the Inconel. Inconel, you know that it is basically an alloy which can withstand very high temperature without its degradation, because you cannot use anything which will react at that temperature with oxygen. So, one thing is the stainless steel SS, another is the Inconel. One is stainless steel, another is the Inconel that you can use. On the susceptor, you have to place the substrate. So, this is the substrate, this is substrate which is placed on the susceptor, and then through this gas inlet you have to send the various kinds of gases which you need for a particular type of film deposition. So, if you would like to make silicon, then what type of gas you have to use? Say silane you can use, an example. Okay. So, you have to inject silane which will be decomposed in the reactor chamber. Then where should be the heating elements? The heating elements will be outside the reactor chamber. We want to heat this susceptor and this substrate. Okay. That means, if it is better if you can heat it locally. Why? Why the local heating is recommended? It is because if the whole volume of the reactor chamber is heated, then before reaching onto the substrate surface, reaction will start. Reaction will start. So, on different parts of the reactor chamber, there will be the reaction. There will be the reaction, but that will be a loss for you. Material will be lost, because you want the film to be grown on the substrate surface only. Okay. So, that is the reason that you have to control the temperature in such a manner, so that the maximum heating takes place on the substrate region. You cannot avoid, but in those cases, in those parts of the reaction tube, the heat can be kept at a minimum level, so that no reaction takes place. That is known as the gas phase reaction. When it enters in the reaction chamber, we want to avoid the gas phase reaction. Okay. In CVD, what happens? Adsorption takes place. What is adsorption? Do you know what is adsorption? Have you heard the term adsorption? ADSORPTION. Have you heard the term adsorption? What is adsorption?
Attachment of atom at the surface, but not completely bonded.
Yes, very good. Atoms or molecules. Atoms or molecules, arrangements of atoms and molecules on some surface of the material. That is known as the adsorption. So, in CVD, the first stage of the film formation is the adsorption. First, the atoms or the molecules of, say, in this case the silicon will have to adsorb on the surface of the substrate. Then they will react. So, during reaction what will happen? Some solid material will be formed. Those are known as the nucleus. So, if this is your substrate, say, on which the silicon will have to be grown, first there will be adsorption on the substrate surface. Then at that temperature some reaction will take place, and in some parts there will be some solid material that will be formed on the surface of the substrate. Those solid materials will act as the nucleation of growth. That is the nucleation of growth. They will actually form the nucleus for the whole growth. Then these nucleation sites, with time passes, they will grow, they will coagulate, and finally a film type of appearance will be observed on the surface of the substrate. Okay. So, first thing is the adsorption, then there will be the decomposition of the various constituent gases which are in the vapor phase. At that temperature, some solid materials, particles type of thing will be formed, which will act as a nucleation site for the formation of the whole crystal. When you talk about the thin film, basically it is a crystalline phase, it is a single crystalline film. If the lattice constant of the material matches well with the lattice constant of the substrate, then you can say that it is an epitaxial film. Okay. In this case, in semiconductor technology, the films are very thin, of the order of some micron, in some cases less than that, some angstroms, nanometer type of thickness is required. So, when we talk about this APCVD, that means the atmospheric pressure CVD or LPCVD, that means this reaction chamber, that means this is known as the reactor. This reactor will have to be kept in atmospheric pressure for APCVD. If it is kept at a lower pressure, it is known as the LPCVD. But in PECVD, as the name implies, some plasma kind of arrangements must be there. Okay. Now, what is the difference between this AP, LP and PECVD? Is there any difference? Why we shall resort to LPCVD if APCVD is sufficient? Why? Because you know that for LPCVD you have to use some vacuum machinery here. You have to, what is the difference between APCVD and LPCVD? APCVD you need not to bother about the vacuum, because it is the whole atmosphere. The pressure inside or outside will be the same. But when you talk about LPCVD, that means the pressure inside the reactor chamber will have to reduce. But how it is reduced? It is reduced by some pumping arrangement. So, when you need some pumping arrangement, that means the system becomes expensive, one thing. Another thing is that it becomes complex. So, why you will go for LPCVD? And another thing is that for PECVD more attachments are required. More attachments means some gas must be there inside the reactor chamber. That gas will have to be converted into plasma. For plasma, you know that high voltage or radio frequency bias is required. which is very costly also, and the system becomes more and more complex. So, now we shall compare the characteristics of the film grown by these three types of processes. You have any question? This is the characteristics of different CVD techniques. I do not know whether you will be able to see it. For atmospheric pressure CVD, you see that the advantage is that it is very simple. It is very simple APCVD. It is very simple, fast deposition, that means the growth rate is very high, fast deposition and low temperature. So, this is the advantage of APCVD. Now, if you go for the LPCVD, excellent purity, excellent uniformity, good step coverage, and large wafer capacity. So, what is the difference you see? The difference is that in atmospheric pressure CVD, it is very simple, that we all understand. The deposition becomes fast in APCVD, in LPCVD it is not so faster. Why? Why for LPCVD it is not very faster? Yes, because it is a low pressure growth. It is a low pressure growth, so it will be a slow process. Okay? Because there will be, when it is low pressure, that means continuously you are sucking something from the reactor chamber to the scrubber. Scrubber means where the waste product or the materials are burned before airing to atmosphere. Okay? And in APCVD it is the low temperature you can use. In LPCVD the temperature is not low, it is high temperature that we can use. Why? Because if the pressure is low, then temperature must be high to crack the vapors for reaction. Suppose you are using arsine. So, you have to crack arsine. Cracking arsine means you have to crack arsine into arsenic molecules and hydrogen molecules. Suppose you are using phosphine. So, you have to crack the phosphine, phosphorus and hydrogen, into phosphorus and hydrogen. So, for cracking you must maintain a temperature, okay? Because the cracking efficiency is different for different materials. Another problem is that when you reduce the temperature, a pressure, then you have to make the temperature higher because of the cracking efficiency to be higher. In LPCVD we have written that the purity is excellent. Why the purity is excellent? Because it is evacuated. The reactor chamber is evacuated. So, if you evacuate something, that means there is no air inside. If there is no air inside, that means the purity level will be higher. So, there is some advantage. And another important aspect is that it will have good step coverage. What is step coverage? What do you understand by step coverage? Step coverage means, suppose this is your substrate, the substrate is kept on the susceptor. This is your substrate and it is kept on the susceptor. This is your susceptor. When growth takes place, Generally, the films are formed on the surface, top surface, this surface and that surface. On the side portions, there is no growth. So, that it appears like a step type of thing. This is a step. This is a step. If you take the side view of this thing, this is basically a step where there will be growth, there will be growth. On the side parts, there will be for both AP and LP, but in LP it will be better. Why? Because the growth will be uniform. In this case, one thing I must inform you, that so far as the CVD is concerned, so there must be some PVD. What is PVD? If CVD is the chemical vapor deposition, PVD is the physical vapor deposition. If there is something like physical chemical vapor deposition, so there must be something like
Chemical reactions.
yes, physical vapor deposition. Can you name any technique where physical vapor deposition is used? Yes, but what is the name of the technique? The process is diffusion. Yes, sputtering one technique, evaporation one technique, thermal evaporation, sputtering, pulse laser deposition. So, those are the basically the physical vapor deposition process. The difference between the physical vapor deposition and chemical vapor deposition is that in physical vapor deposition, the step coverage is very, very poor, because you have to, what is the fundamental process inside the physical vapor deposition? This is your material, say this is aluminum. You want to make an aluminum film on say glass slide, glass substrate. This is aluminum, this is glass slide. Okay. So, what is the process? Process is that this aluminum, this is known as the target, this is known as the target and this is the substrate. So, this target will have to be evaporated. So, here also the whole thing is placed inside a vacuum chamber. Why vacuum is used? There are because of two reasons. One is that in vacuum chamber there will be no air, so contamination will be less, okay? And at the same time the evaporated aluminum will be able to directly heat on the substrate. If there is air, then what will happen? Yes, there will be scattering, etc. So, this is the reason that there must be it must be in the evacuated chamber. Another thing is that the melting point of aluminum will be less compared to in air. Melting point will be less. So, that is the reason that the whole arrangement have to be kept inside a vacuum chamber. So, there must be something which will break aluminum from the target. Something means it can be a sputtering technique, it can be electron beam, it can be normal thermal evaporation, it can be by the using of laser. That means it will hit the target, it will hit the target. Where is the target? The target is the aluminum, high purity aluminum. So, when it will hit the target, some aluminum will be coming out. That aluminum will be in the form of evaporated aluminum. So, they will be deposited on the substrate. So, remember that in the chamber there is no whole, the whole volume is not the aluminum vapor. Throughout the whole volume of the chamber, it is not the aluminum vapor, because you are not using any gas. It is not any vapor type of thing. Only a part of the aluminum will be coming out and it will be deposited on the substrate. So, the whole volume of the substrate will not be coated with aluminum, only front side will be coated, a part of it will be coated. So, that is the difference between the physical vapor deposition and chemical vapor deposition. So, the step coverage will be less in physical vapor deposition. Okay. Let me show you that here you see that the main difference between the two processes, that means the chemical vapor deposition and physical vapor deposition, two processes, is the resulting step profile of the deposited film. Resulting step profile of the deposited film. A PVD film, that means physical vapor deposition film, deposits straight down onto the surface. A CVD film deposits evenly on all surfaces at the same time, because in CVD we are using the vapor. The whole reactor chamber is full with the vapor of the constituent chemicals, right. Now, the next thing is that how the step coverage is there. These are the species of the chemical materials. This is the substrate. Yes, you see. What you see? That on the sides there is no film. The red is the film, the blue is the substrate, and the yellow is the susceptor. The yellow is the susceptor, blue is the substrate, red is the film. So, you see that the sides are not covered by any film. So, the step coverage is not good. Now, you see that the CVD, you see good step coverage. All sides are covered with the film here. Okay. See, this is the yellow is the substrate susceptor, blue is the substrate, and the red is the film. So, that is the difference between the physical vapor deposition and chemical vapor deposition. That step coverage is very, very important in case of the film growth. Okay. So, then the next issue is the PECVD, plasma enhanced chemical vapor deposition. In APCVD or LPCVD, from where the energy comes? Because the energy is required for which? One is for the decomposition of the chemical vapors, another is the atoms or the molecules must have some mobility so that they can adsorb on the surface of the substrate. So, for that you need some energy. That energy comes from the thermal energy, because you are heating the reactor. For PECVD, the energy is additionally supplied by the plasma. The energy is additionally supplied by the plasma. So, that is why it is known as the plasma enhanced chemical vapor deposition. Here you see that the temperature is low and good step coverage. Temperature is low and good step coverage. So, if we compare all these three CVDs, you see that for APCVD low temperature, for LPCVD higher temperature, for PECVD again low temperature. So, from the temperature point of view, AP and PECVD have some advantage, but for step coverage PECVD has good step coverage, LPCVD has good step coverage. So, for the so far as the step coverage is concerned, AP is inferior to LP and PECVDs. Another important factor is that LPCVD you can use large wafer. Okay. Now, 25 wafers can be used in LPCVD chamber, but in PECVD chamber only 4 wafers you can use, because the efficiency is less in case of PECVD. Another important thing is that using PECVD, both sides of the substrate of the wafer cannot be covered with film, both sides. In LPCVD both sides can be covered, but in PECVD only one side of the wafer, because in our laboratory we use 1 centimeter by 1 centimeter substrate, but in industry the whole 4 inches, 6 inch or 8 inch wafer is used, because otherwise it will not be cost effective. Okay. So, in some cases, say for microelectronics type of thing, where the metallization is done, do you know how many transistors are there in the IC? Millions of transistors, okay? Millions of transistors, and those transistors must be internally connected, connected with the power supply, because without power supply the transistor cannot be operated. Another thing is that you have to put the signal in the transistors. So, for signal and power supply, all those millions of transistors will be internally connected. How it is done? It is done by metallization, and that metallization is basically layer type of metallization. First layer, second layer, third layer, fourth layer, fifth layer, sixth layer. 6 layers of metallizations are done inside that miniature type of device, and all those layers must be separated by dielectric layers. Why? Otherwise there will be short circuited. Layer 1 metallization must be covered by some insulation layer before making layer 2. Then again before making layer 3, you have to use some dielectric layers between the successive metallizations. All those things are done by these processes, CVD or LP, CVD or physical vapor deposition, whatever be the techniques. So, not only that the CVDs are used for the epitaxial film growth, there are other use or application of these CVDs have. So, in that sense the whole wafer is put inside the CVD chamber, particularly for microelectronics type of thing. In PECVD only 4 wafers can be handled at a time, whether in LPCVD 25 wafers can be handled at a time. So, for the cost effectiveness, LPCVD is better than PECVD. So, all the CVDs have their own characteristics. In some cases you will find that the temperature is low, in some cases you will find that the coverage is better, in some cases you will find that the wafer handling capacity is better in LPCVD than APCVD or PECVD. But there are some disadvantages also. One disadvantage is that in APCVD it is very simple, but contamination is there because we work in atmospheric condition. In LPCVD deposition rate is slow and also the temperature is high compared to APCVD. And for PECVD chemical and particle contamination is there. Why? Because for making the plasma you have to use some gas. For making plasma you have to use some gas. So, the chemical and particle contamination will be there. Now, what is plasma? Do you know what is plasma? Plasma is the fourth state of matter: liquid, solid, gas and plasma. So, you see that Yes. You see that the states of matter can exist in 4 different states. One is the solid, then liquid, gas and plasma. In this diagram, we have taken the help of water molecule. You see that the in a solid state, this material is known as ice. Which material? Water. The molecules are all connected to each other, giving it a rigid structure. Yes, giving it a rigid structure. Solid, it is solid, it has some rigid structure where the molecules are bonded tightly to each other. This is the oxygen molecule and these are 2 hydrogen, H2O. It has a structure, you see, it is a rigid, closely packed structure. Then for liquid, you see that the bonds are not so tight now, but there is still some structure there. So, that means if we explain this thing, if it gets heated up, which one? Ice. The molecules get some energy, obviously. The ice melts and become water. It can be held in an open top container, that means the lid is not closed. You need not to use a lid for keeping water, it is not a vapor. For vapor you have to put some lid, otherwise it will, what will happen? It will go away from that container. But for water, it can be held in an open top container, that means there are some structure, though not rigid, but there is some bonding of the molecules. That is why it can be kept in an open top container. So, that molecules still have some connection to each other, giving it some structure. If the water is placed in a kettle and heated again, it will turn into steam, which is a gas. The molecules have lots of energy and break away from each other. The steam cannot be contained in a vessel unless it has a lid. Okay. So, that means it is completely randomly it is moving. You see that in gas, bonds do not exist between the molecules anymore and all structures is gone, right. So, from solid ice to gas, we find that it is basically the game with the structures. There is no rigidity, there is no specific structure. So, they can move anywhere. Then the next part is the plasma. Finally, if the steam is given immense more energy, the steam which you have done earlier out of your heated water, the single molecules themselves break apart into their constituent elements. This is known as the plasma state. Okay. So, you see that in this case the bonds within the molecules are now broken. Here you see the difference between this thing is, in gas H2O steams were there, oxygen and hydrogen were still bonding. In case of plasma, the oxygen and hydrogen molecules are part apart, there is no bonding, right. So, similarly, in normal PECVD, plasma enhanced chemical vapor deposition, argon is used as a gas, right. So, if you use some RF power supply, high voltage, then what will happen? The argon plasma will be there, that means there will be argon ion and electrons. Argon ion and electrons, it is not water that it will break into hydrogen and oxygen. In argon what will happen? There will be electron and there will be positively charged ion. that positively charged ion argon will collide with the say aluminum. So, if it collides with the aluminum, then it will remove some parts of the aluminum because of its energy. And what will the electrons will do? The electrons will no, there is no oxygen, because it is under complete vacuum. First you vacuum it, then you send some argon. So, that argon there is no oxygen, etc. So, you make the argon plasma, then you make the whole thing. So, there is no scope for oxidation. The electrons are very energetic. So, the electrons will again bombard the argon ion, argon atom basically, and it will ionize more and more argon gas into ions. So, that is fundamental principle of the plasma enhanced CVD. The efficiency will be very, very high, because you are making plasma, then you are breaking the target, large chunk of the material can be removed from the target, because the impact will be higher, and then you can deposit onto some substrate. The chunk of aluminum will fall on the substrate. The substrate is kept in the in a platform below the target. The target is at the higher end. Okay. So, the structure is like this. Say this is your target. Target means the material which you would like to deposit. It can be any material, it can be oxides also, it can be aluminum oxide, it can be zinc oxide, it can be silicon, it can be aluminum. If you want to make some metal film, so what you do? You have to use some metal target. Suppose you want to make gold plated something, that means you want to make gold film, then your target will be gold, high purity gold. Suppose you want to make say a barium titanate film, so what you will do? Your target will be barium titanate, pure barium titanate, and here on the platform there will be your substrate on which you would like to make the film. So, as the ion bombardments will be there on the target, chunks of target will fall on it, and finally, a film will be deposited. Right. Now, you can ask me, sir, why the argon ions will move towards the target? Why the argon ions will move towards the target? Because of the potential, yes. It is always kept in a positive potential. Okay. Sorry, negative potential. So, the neutral or the positively charged particles will move towards that end. So, it will collide with that, and large chunk of the material will be removed from the target and will fall on the substrate to give a film type of appearance. So, this is the
if we want to grow silicon nitride, then we have to use ammonia instead of nitrogen.
that you can, because that is the you see that it depends on the material. Argon is a normal example, not that for all the cases we have to use the argon. Generally for metal film argon is used, but if you want to make some new type of film, say silicon nitride you want to grow, so you have to use ammonia.
So why not nitrogen?
You can, but for making the plasma some tricks are there. So, plasma you have to grow, okay, and its reactivity, that is the whole thing. Why you can use nitrogen also, if it is possible to make the plasma out of nitrogen with greater efficiency than ammonia, with greater reactivity than ammonia, because for cost effectiveness and easy handling procedure you have to use some optimization technique. Theoretically you can do anything, but for optimization you have to use some specific gases and specific chemicals. Okay. So, now you see that for this CVD, I have shown some steps involved in CVD process. This is the susceptor, this is the wafer 1, 2, 3, 4, 5, 6, 7. I shall explain all those 7 steps in the next slide. Okay. Process 1, this arrow means it is a gas stream. Gas stream means the vapor containing the chemicals which are required for the fabrication of the film. One is transport of reactants by forced convection to the deposition region. Number 2, transport of reactants by diffusion from the main gas stream through the boundary layer to the wafer surface. Number 3, adsorption of reactants on the wafer surface. Number 4, surface processes including chemical decomposition or reaction, surface migration to attachment sites, site incorporation and other surface reactions. So, number 4 is basically related to the surface processes. There are many surface processes which are involved for fabrication or making of the film. Then what is 5? 5 is the desorption of byproducts from the surface. Number 6, transport of byproducts by diffusion through the boundary layer and back to the main gas stream. Number 7, transport of byproducts by forced convection away from the deposition region. So, these 7 steps are involved in any CVD process. So, let us start from 1, transport of reactants by forced convection to the deposition region. Suppose you have to use some silane for silicon deposition. So, that means in one some silane is involved with some high purity gases, say with hydrogen, because there must be some carrier gas. So, one is the transport of reactants, in this case it is the silane, the reactant gas is the silane. Who is transporting? Hydrogen, or you can use silane itself if it has sufficient quantity with you, but silane you know that it is very dangerous gas and very costly also. So, generally we use some hydrogen mixing. Then number 2 is the transport of reactants by diffusion from the main gas stream. Main gas stream means is hydrogen plus silane. From the main gas stream, diffusion of what? Diffusion of silane on the silicon surface. So, diffusion from the main gas stream through the boundary layer to the wafer surface. Okay. Then adsorption, that means the molecules or the atoms are resting on the surface of the wafer. Then number 4 is the surface process. This is very complicated process and it includes, what is surface processes? It includes many things. One is the chemical decomposition or reaction, because the temperature of the wafer is higher than any part of the reactor, because you see that the heating is done on the susceptor, just below the susceptor. So, the temperature is higher in that region compared to the other parts of the reactor. So, it will be chemical decomposition or reaction. Surface migration, that means from migration means moving from one part to the another part, movement. Site incorporation and other surface reactions. So, the whole thing is basically 4. 4 gives you the shape of the thin film on the wafer. Number 5 is the desorption of byproducts from the surface. Byproducts mean when silane is converted into silicon. So, there may be some byproducts. I shall show you some reactions in the next class. So, what are the byproducts for a particular type of thing that I shall give some example in the next class. So, those byproducts will be desorption from the surface, then it will be transported to the main gas stream. What is the main gas stream? Main gas stream is hydrogen plus. Okay. So, here also there will be hydrogen plus silane, here also hydrogen plus silane. So, only some parts of the silane will be diffused onto the surface and many parts of the silane will be go away from the reaction chamber to the vent or the waste. And number 7 is the transport of byproducts by forced convection away from the deposition region. Okay. So, this is the inside view and different processes related to the chemical vapor deposition of any material. Only thing is that your gas will be different, your reactants will be different, your byproducts will be different, but the process is same and the main process is process 4, that means the surface process, which actually will make the film and will give you the shape of a film. Okay. So, now there will be different kinds of reactor design. One is say the atmospheric pressure versus low pressure. What are the advantages of low pressure? You see that we have discussed something, but some more discussion we can make like this: the elimination of parasitic nucleation in the gas phase. What is parasitic nucleation in the gas phase? Parasitic nucleation in the gas phase means before coming to this reaction site, this is the site of the reaction. On the surface of the substrate there will be reaction, that means step 4. Okay. That means step 4. Before making some reaction in the step 4, there may be some reaction here and there. That is the parasitic nucleation. We want that the whole nucleation takes place on the surface of the substrate. So, if you use low pressure, then it will eliminate parasitic nucleation in the gas phase, reduction of out diffusion. Out diffusion means, what is out diffusion? Out diffusion means something from the substrate, diffusion something from the substrate. Say you use gallium arsenide, say diffusion of arsenic from gallium arsenide to the gas stream, that is out diffusion. Reduction of auto doping, improvement of interface sharpness and impurity profile, lower growth temperature, thickness uniformity and compositional homogeneity, elimination of memory effect. Those are the important things that one must take into consideration before designing of a reactor for CVD. I shall come to that point also, what is memory effect. What is memory effect? Memory effect is the presence of vortices, that means behind the susceptor, and dead volumes, sharp corners in reactor inlet, acts as sources of unwanted materials which cannot be removed easily. One is the behind the susceptor, that means you see that this is the susceptor, behind the susceptor means in this region, and another is the dead volumes, that means sharp corners in reactor inlet. So, this is the inlet, that in inlet there will be some sharp corners like that. I can show you one reactor of a CVD how it looks like. If you come to my laboratory, I can show you that it is a quartz type of reactor and there are many dead volumes, that means there are many sharp corners in the reactor inlet. So, where the unwanted materials cannot be removed easily, it cannot be removed easily from the space behind the susceptor and also at the sharp edges of the reactor. During the growth of sharp heterojunction and steep doping profile, by switching a flow with another chemical composition, the original composition is still present in the vortices and trapped gases. That means, suppose you want to make indium gallium arsenide on indium phosphide. So, first you grow indium phosphide, that means when you are growing indium phosphide, indium and phosphorus are coming inside the reactor chamber. Then as soon as you would like to grow indium gallium arsenide, what is the next step? The next step is that switching over from phosphorus to gallium and arsenic. That means phosphorus will be stopped and at the same time gallium and arsenic will make the input. So, this is switching. Again you want to grow indium phosphide, then what will happen? Gallium and arsenic will be stopped, phosphorus will be on. So, this is the changing or switching, and if there is a dead space or dead volume inside the material, though you switch off phosphorus, there will be some trace amount of phosphorus inside those places. So, that means here the material will be indium gallium arsenide phosphide, because there will be some phosphorus. That is the memory effect. You cannot remove the phosphorus instantly. That is known as the memory effect. And the slow out diffusion from these parts will smear out the doping or the heterojunction profiles. That means now the profile can be like this. You want sharp profile, say this is gallium arsenide, this is gallium aluminium arsenide, then again it is gallium arsenide and so on. This is the step profile. Now, if you switch off arsenic and make an input of aluminium, if it is instantaneous it is okay, otherwise what will happen? There will be like this. This thing is not sharp, right? There will be gallium, aluminium, arsenic. Here also there will be aluminium, because if you remove aluminium, because of the memory effect, some aluminium will be there. So, that is the memory effect, and this can be eliminated by rapid evacuation, that means working at low pressure. So, that is the memory effect. So, this is the advantage of LPCVD. Okay, thank you.